Welcome back to Applied Physics. In this video, I want to talk about free body diagrams, which are honestly a very simple concept on their own. So really what I want to talk about is how we can use free body diagrams to introduce new ways of solving problems involving forces. Let me get my head out of the way. The idea of a free body diagram is incredibly simple. If we have a situation, let's say that we are dealing with an inclined plane. So we have a tabletop surface here. We have a plank of wood that is being supported by some leg of some sort, which puts that surface at an angle. Let's call that angle theta. And we have a car that is on this inclined plane. Well, there are several forces that are happening to this situation. The obvious ones, we have the weight, force of gravity, which is always pulling downward. There is going to be a normal force, which is always going to be perpendicular to the surface that it's on. And maybe there's one other thing happening here. Let's go ahead and put a pulley at the top of this and run a rope with a counterweight going down over that pulley. Well, in that case, going along the rope is a tension force on the rope, or maybe an applied force depending on how you want to think about it. Regardless, the important thing here is to recognize that this is a very complicated picture. There's a lot happening here, and when it comes to analyzing the forces, most of it's not really all that necessary. So the goal of a free body diagram is to simplify this picture and keep only what we need. We have an object. I'm going to represent that object as a dot. We have a couple of forces. Tension, normal, and gravity. We also have an angle. Although before I even think about the angle, I want to think about the fact that the tension and the normal force, as I've set it up, are at right angles to each other. So I'm actually going to set up my coordinate axes on an angle. There is nothing that says that your coordinate axes have to be set up with the y-axis vertical and the x-axis horizontal. There's nothing that says you have to be set up going to the left or to the right. Well, let's go ahead and call this the x-axis, and let's call this the y-axis. Now we might have to think a little bit about the angle here, although it's not that bad. Let's draw this in red, I think. If I continue my dotted line here, there's my angle theta. This is a right triangle, so the angle up here is going to be 90 degrees minus theta, and then this whole thing is a right angle, which means that the angle right here is also going to be theta. Now that I've reasoned that out, I'm going to get rid of those red lines because it's actually just extra stuff that's kind of in the way. No, I said give me yellow. There we go. Now let's go ahead and mark our angle theta right here. The way that I have set this up, the tension is right along the x-axis, the normal force is right along the y-axis, gravitational force is kind of doing its own thing. So the next thing that I want to do is, let's use a thicker line here so we can actually see it. I want to take gravity and split it up. to find the component along the x-axis and along the y-axis. This is a little bit trickier than it appears at first glance because our angle is not given to us in standard position. But if we just think about trigonometry, right, we have a right angle over here, we have our known angle here, so the force of gravity is the hypotenuse, the y-axis is the adjacent leg, so adjacent over hypotenuse is cosine, FGY is going to be FG cosine theta. This bit over here, which we've set up as being with the x-axis, is the opposite leg, so that'll be FG sine of theta. Right? So when you don't have your angle given in standard position, you have to think about things a little bit and try to make sure that everything makes sense. The other thing that I notice here is that these are actually both going to be going in the negative direction. Right? The x and y components are both in what I have set up as the negative axis in that direction. All right, why is my scroll not scrolling? I don't know, but let's just get this taken care of. Now that I have that, the next thing up, I'm going to talk about a net force. In order to talk about a net force, we usually use the Greek character sigma here. So the net force, and I'm going to split this up and think about it separately in the x direction, as well as in the y direction. And this is where the free body diagram is so useful. In the x direction, I've got tension, and I've got the x component of gravity. Those are the only things happening in the x direction. Right? Tension is Ft. Force of gravity in the x direction is minus Fg sine theta. In the y direction, we had the normal force and the negative of the y component of gravity, so Fg cosine theta. If I put some numbers in here, then we're going to be able to get some work done with this. All right, so some things that we might know. We're going to just assume that we're on Earth, so acceleration of gravity is 9.80 meters per square second. We're going to go ahead and set the angle here. Let's set it at 25 degrees. And let's say that we have an object, the car in this case has a mass of 0.800 kilograms. All right, so those are just properties of the setup. And then we have the tension coming from an application. We could figure that out if we really cared to, but I'm going to skip ahead just to get to the interesting parts of this problem. We know that that applied tension is going to come to the effect of 1.50 newtons. And our question is, what is the acceleration the cart is experiencing? I guess on top of that, we have to determine which way is the cart accelerating. Is the ramp steep enough that the cart is going to slide down the ramp? Or is the tension caused by the hanging mass strong enough that it's going to pull the cart up the ramp. So there's a lot of question there we should be able to figure out. If the net force is positive, we set up positive as going up the ramp. If the net force is negative, that means the car is going down the ramp. But before we can even get to that, we have one other fact that we should keep in mind. That one other fact is equilibrium. One thing that you know from your life experience without looking at this experiment at all is that that cart is going to stay on the ramp. It might roll up the ramp. It might roll down the ramp. But it's not going to go flying off into space, and it's not going to fall down through the ramp into the center of the Earth. Those are just not things that can happen. So, we know that the acceleration in the y direction is going to be equal to 0. And since Fy is going to be equal to mass times acceleration in the y direction, that means that the net force in the y direction is also going to be 0. That is very often going to happen. We call that the equilibrium condition. If the object isn't moving, or if it remains moving in constant speed, then we say that the forces are in equilibrium. The net force is 0. Right? And with that, we can really start to get to work. Well, force of gravity is mass times gravitational acceleration. You sometimes have to worry about positives and negatives, but we have the negatives built into our equations here, so I'm not going to put it here as well. But we have our mass, 0.800 kilograms. We have our acceleration, 9.80 meters per square second. We have our calculators. My calculator tells me that this force is going to be 7.84 newtons. Right. With that, my net force in the y direction is the normal force minus Fg cosine of theta. And I know that that has to be equal to 0. We said that over here. So rearranging that equation, the normal force is equal to Fg times cosine of theta. Well, Fg we just calculated is 7.84 newtons. Our theta, if I scroll up, was 25 degrees. And if I punch that into my calculator, I get that the normal force is going to be 7.11 newtons. It turns out that we don't really need that number, right? The numerical representation of the normal force is not that important to us. But it's worth knowing, and it's worth thinking about the fact that that is a thing we could figure out. We can also figure out the net force in the x direction, which is the force of tension minus Fg sine of theta. Remember that our tension was given to us. If I scroll back up here, it's 1.50 newtons. Force of gravity we calculated earlier, it's still 7.84 newtons, and theta is still 25 degrees. Not quite enough space to write that in, but that's okay. You know what it's trying to say. All right, so if I take 1.50 minus 7.84 times sine of 25, my calculator gives me the result here of negative 1.81 newtons. This is the net force in the x direction. And that's almost what we wanted. What we wanted was the acceleration. Let me scroll back up here and remind us of what's going on. Right? So negative in the x direction means going this way, which is a reasonable result. The mass that we have hanging here is not sufficient to pull the cart up, so the cart is going to roll down the hill. The acceleration is going to be given by the force. Our mass is 0.800 newtons. We've used that already. But we know that force is mass times acceleration, which means that acceleration is force over mass. In this case, that's going to be negative 1.81 newtons over 0.800 kilograms. And when I punch that into my calculator, I get negative 2.27 meters per square second. All right. And so there we have it. There's a lot of things that we can calculate once we start thinking about the way that our forces are reacting with each other and compounding with each other, and finding the net force in order to find the overall acceleration. Related to this, one other idea. It is more common than you would think to try to design a setup to force equilibrium. A classic example is in what's called a mass spectrometer, where you have a charged particle moving through a magnetic field. The particle is going to be subject to the force of gravity. It's also going to be subject to a magnetic field, a little bit beyond the scope of the course to calculate exactly what it is, but if you have a charged particle moving through a magnetic field, it experiences a force. And then very often what we want to do is set up a third force acting on this charged particle, which will put everything in equilibrium. We call that extra force the equilibrant of the system. So let's take a look at a particular example. Let's say that we have a system with two forces acting on it. We'll call them F1 and F2. F1 is going to have a magnitude of 5.00 newtons, and F2 is going to have a magnitude of 3.00 newtons. I'm going to set up my coordinate axes in standard position because, well, I have to choose something, and I don't really have a good one or the other here. But let's go ahead and call this angle 60 degrees. F1 is going to be right on the negative y-axis. F2 is somewhere between the axes. So we can break F2 into components. Because this is in standard position, f2x is going to be f2 times cosine of theta. Put that into my calculator and I get f2x is 1.50 newtons. f2y would then be f2 times sine of theta. Which, if my calculator will cooperate with me, is 2.60 newtons. The resultant is just the sum of these vectors. Right? A couple of ways I could set this up. I'm going to go ahead and write these in component form. So F1 was along the y-axis. Its x component was 0. Its y component is 5.00 newtons in the downward direction, so we'll make that negative. F2 had x components of positive 1.50 newtons and positive 2.60 newtons. So, adding these together, we get a resultant vector which has components 1.50 newtons and negative 2.40 newtons. If we want this system to be in equilibrium, we want the net force to be 0. The current net force is not 0, it's 1.50 newtons, negative 2.40 newtons in component. If we add one more force to this, which is exactly the negative of that force, then we will have our system in equilibrium. Everything will be equal to 0. Right? We want resultant plus equilibrant to be equal to 0, which means that the equilibrant has to be the negative of the resultant. In this case, that's components negative 1.50 newtons and positive 2.40 newtons. If I go back up to my free body diagram and I roughly sketch in what that resultant is going to look like, it will make sense. Right? Our equilibrant is kind of over in this way. And visually, sure, it looks like if we set the size of that exactly right, that these three vectors will be in equilibrium. The forces will all cancel each other out. The particle will not move. Of course, components are an odd way of looking at a force. So the last thing I want to do is change this back to be a magnitude and a direction. We've done this before. Take the square root of the squares of the components. I get that the magnitude of this force is going to be 2.83 newtons, and then the direction. Take the inverse tangent of y over x, ignoring positives and negatives. Right, I get 58.0 degrees. But then remember that that's this angle. And in standard position, what we really want is this angle, which is going to be 180 minus 58, which comes out at 122 degrees. All right. So we understand that we can think about forces using vectors. We understand that equilibrium is the condition where the particle is not accelerating. Right? Not accelerating is not the same thing as not moving. And we understand that if we want that condition of equilibrium, the net force has to be 0, and we can figure out mathematically a way of calculating what force needs to be added in order to ensure that result. A lot of ground to cover here, a lot of calculations. Hopefully none of it's that difficult. Really, none of it should be new. It's just putting it all together. But I think I've gone on long enough, so I'll wrap up with that. Thank you as always for joining me, and I'll see you next time.